Okay, so I was reading this research paper on object tracking uh, by Alper Yomez, Omar Javed, and Marbar Shah. And I was just reading this point detector section, and I was just thinking about it. So there are 4 point detector mentioned algorithm in the paper: the Marvick detector, Harris detector, SIFT, and the affine invariant point detector. I'm not going to go into detail, and they are complicated. And here's the result of the point detection algorithm here. And when I was looking at it, I saw an interesting problem, which is given an image of an object, can we match it to an internal 3D model? So, for example, this image on the left, which is a Harris detector algorithm. It's an image of common household item, where the spray paint can, a calculator, some clothes, some box, and a jug of maybe cleaning supply. And say we look at this jug, can we match it to an internal 3D model? That's a question. That's a problem. I thought it's kind of interesting. So I want to go through the exercise to figure out how we can do it. So about the 3D model, since we're trying to map this thing to an internal 3D model, what kind of 3D model are we? Kind of data are we going to play with? So the 3D model looks like this, and it has vertex and 4 vertex or 3 can create a face, right? Yeah, a face. And those are in a file as the vertex coordinate, and how the face is constructed from the vertex. So that's what we're dealing with. And how do we map the detected point to the 3D model? Well, the 3D model can have ranging from a few thousand vertex to a million. Depends on how smooth and detailed the model is. And to match every point to the model is going to be very expensive computationally. So maybe we can do some kind of quantization on the level of detail of the model. I was thinking of a 3-level scheme, where the first model with the lowest detail amount will be just a cylinder with correct aspect ratio that will define the bounding box for this jog. And then the level 2 will have the funnel shape and the handle on the top roughly specified. And then the third level, which is the most detailed model, will have all those surface precisely modeled, and those handle and those cab, and yeah, that's a detailed model. And then we can try to map the point to the bounding box first, level 1, and then if it matches, we can map with the level 2, which have the funnel, and then eventually the level 3, if it all matches, we can detect it. Great. So then the question becomes, how do we map those points to a cylinder model, the lowest level of detail? Should we go with a bottom-up approach where we have 1 point and then try to map it to the cylinder? There isn't an obvious way to do that, because 1 point is just 1 point. It could be anywhere on the model or not on the model, and it could be in the bounding box on the exact vertex, or it could be not on the vertex, it's just on the contour. So 1 point isn't enough. What about 2 points? 2 points still has a problem where we don't know exactly where the point is on the model and whether it's on the model or not. So instead of this bean counting point by point adding, we should probably look at the cluster of detected point or segment of the image, and If we have an outline of the image, we can generate a 2D shape from our 3D model, internal model, and compare with the detected segment and classify. But to generate a 2D shape from 3D model, we still have the orientation and scale issue. How big the model should be scaled. That way we can match it. So we can also quantize the orientation. So for example, we have 3 axes x, y, z, and we have rotation. We can quantize the rotation to 90, 180, 270, and 360 degree. That's 4 orientation per axis, and for 3 axes, 4 to the power 3 is 64 possible orientation. But for scale, there are infinite amount of scale, and we can't really do anything. And there's no obvious way to quantize it. Well, we can. We just need some prior knowledge to say, okay, this is not going to be bigger than this scale, and this is not going to be smaller than this scale in the image, and then we just use that. So if we have the scale and orientation, then we can render the 3D model to generate a reference image, and then if we have a cluster of interesting points, we can check how much points that are fallen into the reference image area and then generate a hit rate. And if it's above hit rate, we can classify this as okay, this is a jog, and it matches with the 3D model. And we know the orientation and scale the thing is in the image, and where it is in the image. There's quite a bit of quantization. How are we gonna speed that up? So there's another interesting point, because notice it's a very parallel process in nature. It's the same image. We just need to pass it through multiple different filter or check of orientation and scale. Then we can just do that on a multi-thread Python script or multi-core processor to speed this up. And some other point I noticed is that we can, when humans look down at the surface, they can recognize a circle as a jog caps, and then they'll give us some information on the orientation, that being we're looking down at the jog, and the scale, that okay, this is a jog cap, and that's how big the jog is roughly going to be. And that way we can quickly eliminate all the possible orientation and scale. Just give me one, because we know this is a hint, and then the human will bend down to see the front face of the jog and then classify it as okay, it's a jog. So if we can apply the same principle to figure out some basic shape in the image and then use that to match with the 3D model, then we can potentially speed up things. Okay, to summarize, we had a problem. Given an image of an object, can we match it to an internal 3D model? Well, the solution depends on whether we can have the prior knowledge of scale and orientation. If we have the scale and orientation, and we have detected interesting points, just 1 or 2 points won't do anything, and we actually need a cluster of points, and you can use that to compare with the model, internal model's contour, and classify.